So I'll start by explaining what the title is about, since there's a lot of words. So we're looking at pairing-based signatures. And there are three different types of pairings you can have. And by a unified signature, we mean we unify all these groups. We actually construct one signature scheme that will work in either type of pairing group. So that gives us some conceptual simplicity. Minimal means that, first of all, we get very small signatures, and we can actually prove that they are optimal. As small as they can possibly be, we give low verification complexity. And then as a new thing, we'll also look at the public key size, and we'll get single group element public verification keys, which is also optimal. And finally, they're selectively randomizable. So if we look at a signature, there are basically two variations, two extremes you could be interested in. One is, so the signature has to be existential or unforgeable, so you cannot, given a number of signatures, you cannot forge a signature in a new message. But there's still some space left there, okay? And one desirable feature in some settings is that you cannot even change the signature. So even if you have several signatures in a message, you cannot come up with a new signature on that message. And that's called strong existential unforgeability. You can also, in other settings, go to the other extreme and say, would we actually like the signature to be randomizable? So given a signature, we can randomize it and make it look like a fresh signature on the same message. And in some sense, what we get here is the best of both worlds. So the signatures are strongly existential unforgeable, but the signer can decide on particular messages that these signatures should be randomizable. Okay, and then final word is structure preserving. So let me talk a little about that. So we found some structures that are very useful when we build cryptographic protocols. One example would be cyclic prime order groups. And we've used them to build LGML encryption, Peterson commitments, Schnorr proofs, and so forth, right? And they compose very well with each other, so we can build more sophisticated protocols. An example of a more advanced mathematical structure would be what we get with a pairing. So now we have three groups, say prime order, and we have a pairing that maps two source group elements into the target group. And now we can get even more fancy things, tripartite key exchange, identity-based encryption, short digital signatures, non-interactive zero-knowledge proofs, and so forth. So in structure-preserving cryptography, the philosophy is that we want to preserve as much of the mathematical structure that we can. Okay, so we'll communicate using mainly group elements in the source groups. We'll just use a generic group operation, so multiplication of group elements and so forth. And we'll avoid structure destroying operations, say a cryptographic hash function that messes up everything. And the reason we do this is because it allows us to get some cryptographic schemes that compose very well with each other and preserve efficiency quite well. Okay, so I'll go a little more into details with that now. So the setup we'll assume here is that we have a bilinear group. Okay, so we have groups of prime order P and a bilinear map that maps two source group elements to the target group. And there are three types of these groups. Type 1, where the two source groups are actually the same. Type 2, where they're different, but there's a map from one to the other and homomorphism. And finally, the case where they're different and there are no homomorphisms between them. So this is also known as symmetric setting because the two source groups are identical. And the advantage here is that it's conceptually simple, and we see a lot of protocols built in this setting for that reason. And the other important case is the type 3 setting, because that's the most efficient setting. So structure-preserving signatures will have a setup that describes a bilinear group and also gives some random group elements. And everybody will be working over the same bilinear group. Okay? Then the verification keys are group elements in the source groups. The messages are group elements in the source groups. The signatures are group elements in the source groups. And we'll do verify signatures by checking a number of pairing product equations. So we'll pair some elements, multiply them together, and check equality. And I'll just illustrate that how well they compose with other structure-preserving primitives. Okay? So for instance, LGML encryption is also structure-preserving, right? And since signatures are just group elements, it's easy to encrypt signatures. Non-interactive zero-knowledge proofs, again, we can build them with pairings. And since we just have group elements, we're just working over group elements, that's exactly what these proofs do very efficiently. Or you can go the other way and say, look, I mean, the ciphertext, the proofs, they're just group elements, and it's very easy to assign them. So one nice thing that you get from this mathematical structure is we can actually give some lower bounds on how efficient schemes can be. And in particular, when it comes to signatures, we can prove that a structure-preserving signature needs to have at least 2 verification equations, and that it needs at least to have 3 group elements in the signature. So this was known for the type 3 setting, but it was not known in the type 1 setting, the symmetric setting where the 2 source groups are the same. And a priori, you could think that it could go either way, right? You could think of, look, since it's a symmetric setting, we can mix and match elements and put them both on the left-hand side, on the right-hand side of the pairings. It gives us some extra flexibility when designing the schemes, and we could hope that we could get a lower bound and more efficient signatures. Or you could think of it the other way around, that the adversary now has this ability to mix and match, and therefore we would actually need more group elements to construct structure-preserving signatures. But it turns out that we get exactly the same lower bound as we get in the type 3 setting. And I'll just sketch why that is the case, okay? So first of all, I said that we need at least 2 verification equations. The reason we cannot have a single verification equation is simply that, well, if we have 2 signatures, you can solve and look at all the solutions, and you can always find a signature on the 3rd message and forge that. Okay. Second is an observation that every message must has many signatures, a super polynomial number of potential signatures. Okay? And the reason for that is if we have a signer that just uses generic group operations, it must take some linear combinations of group elements in the setup and in the message. Okay? And if there are only very few possible choices for the signatures, then it uses the same exponents over and over again. And we might simply take linear combination of the signatures, and we'll get signatures on new messages. Okay? And now we can use that to show that a signature needs to have at least 3 group elements. So suppose there were just 1 or 2 group elements. Well, we have at least 2 verification equations, so that gives us 2 equations in 1 or 2 unknowns, these unknown group elements for the signature. And that has at most 4 solutions for any given message, and therefore we would run into the problem above that we cannot have quasi-unique signatures. So a signature must have at least 3 group elements. Okay, so now we've established the lower bounds. We give a matching construction that actually matches exactly that. Okay? So we'll have a setup, so that consists of a description of a bilinear group and some random group elements, in this case just 1 single group element. And the key generation returns a verification key, which has the secret key is a discrete logarithm of this verification key. And the signature, given a group element here, outputs 3 group elements that constitute the signature, calculated like this. And here are the 2 verification equations, and if you plug in these things in, you can see that it is correct, and it verifies as being correct. So this signature is strongly existential unforgeable under adaptive chosen message attack in the generic group model. Now, I know that some people are not fans of the generic group model, but in some sense, we cannot avoid having to make this kind of assumption, okay? Because, so essentially what we end up with is we rule out all trivial attacks by showing that it's secure in the generic group model. But the assumption is still essentially that, look, here's a signature scheme, and we assume that it's secure, okay? But we cannot get around that. I mean, we need to have this type of interactive assumption. And we can actually prove that, at least in the type 3 setting, if you want to base security on a non-interactive assumption, then you need at least 4 group elements in the signature. So here's a really hard trade-off, right? Either you get a good efficiency or you get stronger assumptions, and you have to choose. Okay, so this is optimal, right? Because the signature has 3 group elements, and we have 2 verification equations. And what was known before was to get this optimality in an asymmetric setting. The new thing here is that we get optimality as well in the symmetric setting. And I think that's interesting, right? Because it shows that the attacker's extra capability in the symmetric setting, that it can mix and match group elements, does not lead to larger signatures. Okay? And interestingly, it didn't have to be that way. Actually, for one-time signatures, the picture is different in the asymmetric setting and the symmetric setting. In the asymmetric setting, we only need 1 verification equation, but in the symmetric setting, we do need 2 verification equations. Okay, so another thing that's new with respect to minimality is that it's a minimal verification key, right? I mean, we just have a setup, and then we have a single group element verification key. So, and this is something that hadn't been really considered before, what would be the smallest size of the public verification key, but that's of course also an important parameter. And I think it's important, particularly important, to get down to just 1 group element. And the reason for that is that it becomes very easy to build certification chains now, right? Because we can have a 1 group element verification key that is used to sign a 1 group verification key, which is used again to sign a 1 group element verification key, and so forth. Whereas if the verification keys had been, say, 2 group elements, we would get an explosion when we build that certification chain in the size of the signatures. Okay. In the symmetric setting, this is known as automorphic signatures, because the verification keys can be signed. In the asymmetric setting, it's not really automorphic because the verification keys and the messages live in 2 different source groups. But what you can still build a certification chain just by alternating between the groups, right? So you can use a verification key in G1 to sign a verification key in G2 that can be used to sign a verification key in G1 and so forth. And that way you get your chain. Okay, so let me move on to why this is a unified signature scheme. And the reason is that we really separate the elements and the operations in these 2 source groups, G1 and G2, right? So if you look at, for instance, the signature element S, it only appears on the left-hand side of the pairings. We never use it on the right-hand side of the pairings. So we really keep the group elements separated, but these elements belong to the left-hand side, the G1 side, and some other group elements belong to the G2 side, the right-hand side for the pairings. And that means that the same signature scheme works both in symmetric groups and in asymmetric groups, right? In asymmetric groups, you have to have this separation. Symmetric groups, you didn't have to have it. But since we have it, it works in all settings. And security, on the other hand, also holds in all types of groups. So the most difficult setting to prove security is a symmetric setting where the adversary can mix and match. But even this strong setting where the adversary can mix and match the group elements, it still is secure. Okay. So I think there are 2 reasons why you would be interested in these unified signatures. One is, of course, the conceptual simplicity, that you would just have 1 scheme that works in all settings, all types of pairings. But I think there's also the advantage that we get some resistance against cryptanalysis, right? I mean, it might be that we use this scheme in the asymmetric setting because that's the most efficient setting. But even if a cryptanalyst come along and discover some efficiently computable isomorphism between these two groups, then the scheme will still be secure because that would just map the asymmetric setting into now the symmetric setting. But even in symmetric setting, we have security. And I think an interesting open problem is then, are there other types of schemes where we can get these unified constructions, say encryption, commitment, and so forth. Okay. And finally, I want to talk a little about randomization. Okay. So again, we have two security notions. One would be strong existential unforgeability. So you cannot forge a signature on a new message. And also, you cannot change a signature on a previously signed message. And the other extreme would be that we have existential unforgeability, that you cannot forge a signature on a new message. But you can randomize a signature on a previously signed message. Okay? And we actually have perfect randomization where randomized signature looks exactly like a new, fresh signature on the message. And both of them have their uses. And what we would like to get is the best of both worlds. Okay? And we do that in the following way, that the signer can make a randomization token for a given signature, okay, which makes it possible to randomize the signature. And now the signer can decide whether to give that randomization token along with the signature or not. Okay? So if you don't have the randomization token, you cannot randomize. If you have the randomization token, then you can randomize. And that leads to a security notion, strong existential unforgeability under adaptive chosen message and token attack. Okay, so the adversary can get signatures with or without tokens. Okay, still cannot, of course, we have existential unforgeability, cannot forge a signature in a new message. And also it cannot create a new signature on a previously signed message unless it has a randomization token. Of course, it has a randomization token, then it can randomize the signatures. Okay, and the construction for that is also really simple. Okay, the randomization token is just one single group element. And you can then randomize using this procedure here. So you can see here we take the element R to 1 over alpha and S to the, take S prime to be S to the alpha, right? So this 1 over alpha and the alpha will cancel out with each other here. And then here we have here some alpha square and so forth to make this second verification equation work. Okay. So to summarize, right, we have this really simple structure-preserving signature scheme. It's minimal. It has 3 group elements. The verification key is just 1 group element. And the verification takes place using just 2 pairing product equations. It's unified. It works for all types of pairing groups. And it's selectively randomizable, so we can choose on a message-by-message basis whether we want to have strong existential unforgeability or to release a token and make it randomizable. Okay, thank you. I think not. I mean, so often you can transform the interactive 3-group element signature into a non-interactive 4-group element signature. However, you do lose randomizability. That you don't get perfect. You get kind of partial randomization, but not perfect randomization. There's some 1 group element which you cannot randomize. So that's one change that you would have. And let's see, the verification key would also grow with 1 group element in that construction. 1 or 2, I don't remember. So you don't get quite the same properties. I would expect that to be the case, though let me not be 100% sure about that right now. Yes. Thank you.